theory, guiding channels, etc. Currently, 7 scholars are working under her guidance, and she has published more than 120 research papers in various international journals and conferences. She has completed 5 research projects under MHRD, DRDO, RCI, and DST SERB, and recently she has received one DST SERB project with worth of rupees 33 lakhs and one Spark SPARK project with the worth of 59 lakh. She is a reviewer of various international journals. I would request Dr. S. Anuradha ma'am to please start the session, please.
Yeah, good evening to all. Thank
Good
you for
evening,
your
madam.
kind words, sir. Yeah, first of all, I would like to thank the management of Samskruti College of Engineering and Technology. And also, I would like to thank the coordinators of this wonderful workshop, Professor Vanisri ma'am and Anup Tiwari sir. And
Thank
also,
you.
I would like to congratulate the Department of ECE. Thank you. Thank you for giving me the opportunity to deliver a lecture on diversity combining techniques in wireless communications. So, thank you.
Thank you, madam. Thank you.
Can I share, madam, my screen?
Yes, madam. Yes, madam. You can share.
Madam, is it visible to you?
Yeah, is it visible, madam?
Okay. Diversity techniques in wireless communication is my today's topic. So actually, this is one of the research area in wireless communications like 5G and beyond 5G wireless communications.
Madam, please switch on your camera, madam.
Yeah.
We'll take a.
Okay. 1 minute, madam.
Yes, madam.
Diversity techniques, equalization, fading channels, and modulation techniques or spatial modulation techniques are the areas of wireless communications. Not only these 4 areas, and PAPR reduction techniques are one of the research area in 5G and beyond wireless communications, and resource allocation is the another research area. Then uh, like in the spatial modulation, index modulation techniques and quadrature spatial modulation techniques are also one of the research area, and also error control coding techniques are also one of the research area in wireless communications. So I have given only 1.5 hours maximum. I will try to finish how to design one of the diversity technique. If time permits, I will explain another diversity technique with mathematically. If you know the mathematical analysis and designing procedure, then automatically write a MATLAB program and how it is incorporated in the system. Because here 5G and beyond 5G is actually my research area is wireless communication I am working on under physical layer. First, we want to select any one of the wireless communication system or a multi-carrier system. In that system, diversity is one of the block, how it is incorporating at the receiver side. So that's why first I will explain need for diversity, types for diversity, what is the purpose for using this diversity, and how to design the diversity technique, I will explain. So first, just I will take 2-3 minutes time. We'll finish the wireless technologies, evolution of wireless technologies. Approximately in 1990s, um, to second generation technology and 2.5 or 2.75 generation technologies. In the second generation technology, after every 10 years, the technology will be changed, and the data rates or the speed and also applications speed can be like it is increased, and the data rate is also increased, and also more number of applications are added in the technology. So here in 1990s, in the second generation technology, just I have given one technology name, but not only GSM and only CDMA is not only the second generation technologies. If other generation technologies also comes under second generation. So global system for mobile, the approximate data rates for second generation technology is approximately 10 kilobits per second. In the second generation, one of the technology is code division for multiple access. Approximate data rates are 10 kilobits per second. And the 2.5 generation technology is global packet radio service. This is also approximately 50 kilobits per second. And 2.75 is enhanced data for global system for mobile evolution, approximately 200 kilobits per second. From compared to second generation to 2.75 generation, the data rates are increases. And compare it to second generation to third generation, again the data rates are increases. Suppose in the third generation technology, one of the technology is wideband code division multiple for access. So in this technology, the data rates are approximately 384 kilobits per second. And again, the third generation, one of the technology is code division for multiple access to 2000. This is approximately 384 kilobits per second. But we go for 3.5 generation technology, and so this is the high speed downlink and uplink packet access systems. The approximate data rates are 5 to 30 megabits per second. And 3.5, one of the technology is EVDO, evolution data optimized technology. The approximate data rates are again 5 to 30. When compared to second generation and 2.5 or 2.75 generation technology, data rates are compared to the third generation and 3.5 generation, the data rates are increases. So approximately in third generation in 2000s. Previously, it is 1990. Now, after 10 years, again the technology is changed, and the data rates are not only data rates. There are many parameters are there. So, but here I have given only data rates. And in the 2000 technology, 3G and 3.5G technology. Coming to in 2010 approximately, the fourth generation and the fifth generation technologies. In the fourth generation technology, not only a long-term evolution, FDMA is one of the technology, OFDM, MIMO systems are also fourth generation technologies. In the fourth generation technology, the data rates are approximately 100 to 200 megabits per second. But previously 5 to 30 megabits per second. But here 100 to 200 megabits per second. How the data rate is increased from third generation to the fourth generation technology. Again, in one more fourth generation technology is WiMAX technology. Worldwide interoperability for microwave access, the approximate data rates are 100 megabits per second. And fifth generation technology is, this is not completely developed, even though now it is in the developing stage. So there are many 5G waveforms. NOMA, non-orthogonal multiple access, UFMC, universal filtered multi-carrier, and GFDM, generalized frequency division multiplexing, and FBMC, filtered bank multi-carrier, and massive MIMO, and MIMO OFDM, and massive MIMO. So these are the 5G waveforms. So in the 5G waveforms, so the approximate data rates are in terms of gigabits. Compared to fourth generation to the fifth generation technology, so the data rates are in terms of the gigabits, 10 to 30 gigabits. So now from 5G to again beyond 5G, again the data rates are increases. But what is the difference between fourth generation and fifth generation technology? Not only in the point of data rates, but actually there are one drawback in fourth generation technology, that is peak to average power ratio is it is more. So that problem can be eliminated. We go for the fifth generation technology. Not only that problem, so even in terms of the data rates, in terms of the speed, in terms of the applications, in terms of the latency and reliability, all parameters point of view, the fifth generation technology, our speed is more. And also whatever drawback in fourth generation technology, that can be not completely eliminated, but it should be something should be reduces. We go for the fifth generation technology. But here in the fifth generation technology, the peak to power ratio or peak to average power ratio is it is the reducing the transmitted power by using 5G. But even in the 5G also, it is we are facing some problems. So what is that problem in the 5G waveforms are complexity of the system. In the 4G technology, compared to the fifth generation technology, in the fifth generation technology, a bank of filters are used, or filtered banks are used. So that is the designing of a filter, not only single filter, it is a bank of filters are used. So that is the overall system complexity is more in 5G. So that's why in the complexity of the system is reduces, we go for the NOMA. NOMA is 5G and beyond 5G wireless technology. So in the current research area is which is the best way for means non-orthogonal multiple accessing technique. So even in the NOMA also, how UAV is incorporated, and RIS, reconfigurable interference surfaces, or how it is incorporated without reducing the reflections by using the RIS elements are used in between the transmitter and the receiver, and UAVs are also used, and also special type of coding techniques are used in the 5G and beyond 5G. LDPC coding techniques and turbo coding techniques are used to reduce the number of errors in the 5G system. So in the 5G, what is the drawback in 5G is complexity, system complexity. To reduce the system complexity, we go for the NOMA. NOMA is 5G as well as beyond 5G. Waveform is NOMA technology. This is the data rate and applications. Actually, initially there is a basic voice and a basic data downloading application for the 2G and 2.5 or 2.7G. 3G to 3.5G, high speed data and video calling and voice is the application, and 4G online gaming, HPTV. So that is in the 4G. Not only 1 and 2, there are many, but I will give you few examples. And the 5G is massive connectivity for new applications for mobile, e-health, autonomous vehicles, smart cities, smart homes, and IoTs are the applications of 5G, and even in the beyond 5G also. And this table is the what is the theoretical speed, technology, and features of second generation, third generation, and all generation techniques. So coming to 5G can be significantly faster than 4G in terms of the speed, and 5G has more capacity than 4G. And 5G is designed to support 100 times increase in the traffic capacity and network efficiency compared to the 4G. And 5G has lower latency than 4G in terms of the milliseconds. So before start the diversity techniques, first of all, in the multipath communication or multipath wireless communication system, what are the challenges? And so those challenges are how it is reduces, how it will increase the wireless communication system link performance is increased. So first we will start some basics of wireless communications. So one is propagation of radio waves. What is meant by propagation of radio wave? So we have a transmitter. This is the transmitter or the base station. The radio propagation is the tendency of radio waves to travel from one point to the another point, or from transmitter to the receiver, or into various parts of the atmosphere is called as a propagation. What is meant by propagation means uh, to transfer the information. Information means in the form of radio waves to travel from transmitting station to the receiving station, or from base station to the mobile. So what is meant by multipath propagation? In the multipath propagation, we have a transmitter and we have a receiver. So in between the transmitter and the receiver, without any objects or without any obstacles in between the transmitter and the receiver, so the signal is transmitted by the transmitter, and the receiver is received at the receiver side without any object. Here we have three objects. One is car is one of the object, and building, and here some pole or electric pole is the, there are some objects in between the transmitter and the receiver. So even it is having the objects, but the signal is transmitted by the transmitter and reaches to the receiver without any object in between that path. That is called as a LOS path, line of sight path. Suppose what is meant by non-line of sight path? There are some reflections, refractions, diffractions. So all these occurs due to objects in between the transmitter and the receiver. So here, so this red line indicates when the signal is transmitted by the transmitter and hits on like or impinges on the some electric pole, and again some reflections takes place and received by the receiver. And here also this path is also, there is a, the same signal is transmitted by the transmitter and reaches to the receiver, or multiple copies of the signals are reached by the receiver, and superposition of all the multiple copies of the signal, whether it is constructively interfere or destructively interfere. So here all multiple paths are, it is a non-LOS paths. One more diagram I will show you. So here also this is one of the path. This is the direct path in between the transmitter and the receiver. There is no object in between this path. So this is LOS path. And the remaining all paths are non-LOS paths. Non-LOS means definitely the distance between the transmitter and the receiver, or distance between the base station and the mobile is a more distance when compared to the LOS path distance. LOS path is the shortest distance path in between the transmitter and the receiver. If you, there is an object in between the transmitter and the receiver, at the receiver side, we have received a signal or multiple copies of the signals are received, definitely the signal strength will be degraded. Maybe in terms of the attenuations will occur. So that is called as a fading, attenuation of the signal in various variables like maybe amplitude or phase or frequency changes or attenuations and delays, if all the signals are not received at same time. So maybe one path signal, this path signal is received by one time, and this path signal is received by another time. So it depends upon the objects in between the transmitter and the receiver, or there are some delays are occur. So because all the multiple copies of the signals are not received at the same time, even receiving one by one path signal, there are some delays or occurs. There is some fading occurs. How to reduce this fading, and how many types of the fadings? So just I will give you the a brief idea, because this diversity is used to improve the performance of the wireless communication link, and also so the fading effects are reduces by using this diversity technique used at the receiver side. So first of all, what is meant by due to the multipath propagation, fading occurs. What is meant by fading means to reduce the signal strength. Signal strength means in terms of the power, in terms of the energies, um, and also there are so many like in terms of the amplitudes also. So the signal strength will be calculated. So the receiver will receive two or more than two more copies of the same signal from different paths received at the receiver side. And so if multiple copies of the signals are received at the receiver side, if all multiple copies of the signals are added, so they are constructively interfere or destructively interfere. Suppose, for example, in this waveform, consider L equal to two path scenario. L is equal to number of paths. There are two path scenario. Consider only two paths. So this is path one, and this is the path two signal. So when the signal is transmitted by the transmitter at the receiver side, the receiver has received first path signal is, this is the first path signal waveform. And the second path signal is, this is the second path signal is received. So just you can observe if the both path 1 and path 2 phases are same and amplitude is also same. So the phase is same and amplitude is same. By adding these two paths signals are summing of the path 1 signal and path 2 signal, the resultant signal amplitude is, this is the resultant signal amplitude. So when we compare it to the path 1 signal and path 2 signal, amplitudes are compared to the resultant signal amplitude. The resultant signal amplitude is more when compared to the path 1 and path 2. So here this is what type of the interference means. It is a constructive interference. Constructive means the amplitude of the transmitted signal is increases. So whereas in the destructive interference means, again consider two path scenario. So this is the path 1 signal and this is the path 2 signals. So path 1 signal is, this is the phase, but amplitudes are same. These two waveforms are received at the receiver side. The receiver has received the first path signal and the second path signal. If the both signals are, amplitudes are same, but the phases are different. Suppose this is the phase and this is the phase, 180 degrees phase difference between path 1 and path 2. By clubbing or combining these path 1 and path 2 signal or summing of the two paths signals, the resultant signal is phases are in opposite phase. Opposite phase means it is destructive interference. If both are added, it is destructively interfere. So what is meant by constructive interference and what is meant by destructive interference? Oh, sorry, 1 minute. Constructive interference and the destructive interference. Uh, so now In the constructive and the destructive interference, how it will occurs means this is the one of the simple scenario L equal to two path scenario. So there are two effects are occurs due to multipath propagation. And coming to fading, what is meant by fading means uh, so the fading is variation of the attenuation of a signal with various variables. What are those variables? Maybe time is one of the variable, and position or frequency and phases are same, or phases are not same. So because if the attenuation of the signal is nothing but a fading. How many types of fading? There are basically two different types of fading, generally classified into two types. One is small scale fading, and second one is large scale fading. So, how this fading is occurs due to multipath propagation of the signal? So, the fading occurs. What is meant by fading means attenuation of a signal due to different variables like delay or time, amplitude, frequencies or changes. So that is nothing but a fading in the signal or faded in the signal. So based on fading, two classes. One is small scale fading and second one is large scale fading. In small scale fading, based on the delay spread, based on the Doppler spread, actually delay spread is one of the channel parameter, and the Doppler spread is actually there are five different types of channel parameters. One is delay spread, and second one is maximum delay spread, and a third one is RMS delay spread, and fourth one is coherence bandwidth, and fifth one is the Doppler spread. These five are parameters of the channel. What are the basic parameters of the channel, and what are the characterization of the channel means delay spread, maximum delay spread, RMS delay spread, then coherence bandwidth, and the Doppler spreads are a channel parameters. So again, the small scale fading is classified into, I will not explain for the channel parameters. So just I will give you what are the channel parameters or what are the channel characterizations. So in the delay spread, based on the multipath delay spread and the delay spread, again the small scale fading is classified into flat fading and frequency selective fading. So based on Doppler spread, again the small scale fading is classified into fast fading and slow fading, and large scale fading. So in the large scale fading, uh, how the large scale fading occurs means due to path loss and due to the shadowing effect. So the large scale, what is the basic difference between large scale fading and small scale fading? Because the diversity is used to reduce the small scale effect and to reduce the large scale fading effects. So that's why I have given the list of classification of or types of fadings, and what is meant by small scale fading and what is meant by large scale fading. Small scale fading means when the user moves over a small distance. So when the user or mobile user or the receiver, if the receivers are not a fixed receivers, if the base station is fixed in the location, but the users are, best example of moving user is our mobile and a car. So they are not a fixed position. So they are movable users. If the user is mobile user is moves over a small distance in between the transmitter and the mobile user, the instantaneous received signal strength like fluctuates rapidly. The received signal strength fluctuates rapidly even when the mobile user moves a very small distance from the transmitter to the receiver. Even in the small distance between transmitter and the receiver, the received signal strength fluctuates rapidly. So it gives rise to a small scale fading. What is meant by small scale fading? How the small scale fading is occurs means this is the reason. When the user moves over a even in the small distance, the received strength or a received signal strength fluctuates rapidly. And so that is called as a small scale fading. What is meant by large scale fading? In the large scale fading, when the user moves over a large distance, because between the transmitter and the receiver, there are a large distance between transmitter and the receiver, even though the average received signal strength gradually decreases. So because here the received strength gradually decreases, but here rapidly fluctuates. So the received signal strength is decreases here, and here it is decreases, but gradually decreases. So that's why for designing of a fading channels or modeling of a fading channels, it does not consider these effects, or a large scale fading effect is not considered, because this fading is neglecting, because the received signal strength is very gradually or slowly decreases, even though the receiving and the transmitter distance is even in the more. So this is the basic difference between. That's why for designing of a fading channel modeling, like there are different types of fading channels: relay fading channel, Russian fading channel, Nakagami fading channel, Weibull fading channel, height fading channels. So all these fadings comes under small scale fading. So because the received signal strength is fluctuates rapidly, how to control the received signal strength? What are the methods or techniques used to control the received signal strength, or how to improve the received signal strength with the help of the diversity technique, or with the help of the equalization techniques are used to improve the received signal strength. So that's why using small scale fading is considered, and designing of a fading channel or modeling of a fading channels. And the non-fading channel is AWGN is a non-fading channel. So here in large scale fading, there are two effects. One is path loss, and second one is a shadowing effect. So here in the path loss means, suppose we have a transmitter, there are three mobiles or a receivers. So in between the transmitter and the receiver, the distance is small. The signal strength will be like the thick line or thick arrow line indicates it is a received signal strength is more when compared to the other receivers. So this receiver distance is actually compared to the, this is receiver 1, maybe receiver 2 and the receiver 3. If the receiver 1 is close to the transmitter, the received signal power is more. And here the second receiver is away from the transmitter, or compared to the first receiver, the distance is more, the signal strength will be decreases. And the receiver 3 is it is far away from the transmitter, so the signal strength will be very less. That's why it indicates, dotted lines indicates it's a the received signal power is less. And what are the propagation mechanisms, or what are the effects when the signal is propagated from transmitting station to the receiving station? Suppose this is, we have a transmitter, and so we have a receiver. So in between the transmitter and the receiver, there is a object. So there are three different possible effects are present when the signal is hits the object or hits the obstacle. There are three different possible effects or happened. One is reflection, diffraction, and scattering. So in the reflection occurs, the propagating wave or the transmitted wave impinges on a smooth surfaces. So if the electromagnetic wave or the propagating wave impinges on a smooth surfaces, reflections are occurs. So this is the smooth surface. And how the diffraction occurs? Diffraction occurs when there are sharp edges between the, when the wave is hits on sharp edges. Actually, here there is a sharp edge. So the diffraction occurs. And scattering. So scattering means when the electromagnetic wave impinges on a rough surfaces. Suppose this is a rough surface or the irregular surfaces. So the scattering occurs. So these three are the three different possible effects are present when the signal is hits on any object. So it depends on the smooth object or maybe sharp edge or it may be a rough surface, whether the reflection occurs, diffraction occurs, and the scattering occurs. So coming to diversity. Yeah, actually here our exact topic is diversity combining techniques. What is meant by diversity and what is the principle of diversity and need for diversity and types of diversity and types of micro diversity is one of the type and macro diversity is the another type, micro and macro diversity and diversity combining techniques. So what is the basic principle of diversity? So the principle of diversity is same information reaches the receiver on statistically independent channels. Suppose we have a transmitter and we have a receiver. In between the transmitter and the receiver, there is only one path. So when the signal is transmitted by the transmitter and this signal is reached by the receiver through a single path, so there may be a deep fade occurs. Actually, deep fade. What is meant by deep fade? So due to the transmission of the signal at any point of time through the channel, maybe if deep fade occurs, the signal will be lost and this link will be completely collapsed. So that's why what is meant by deep fade means through the channel or in between the transmitter and the receiver. So there is a channel in between the channel. So suddenly the transmitted signal amplitude is suddenly decreases. So suddenly decreasing in the amplitude of the transmitted signal is called as a deep fade. How? So the deep fade occurs means there is a sudden dip in the amplitude of the signal is called as a deep fade. Due to the deep fade, the signal link or path or so there is a path or there is a transmission path or there is a link in between the transmitter and the receiver. If the deep fade occurs, the entire signal is lost. So that's why uh, diversity is used to the same signal is transmitted by multiple paths. The same signal is transmitted by L multiple paths. Suppose if the deep fade occurs maybe in the two paths, suppose this path deep fade occurs, maybe here deep fade occurs. By removing these two paths and the remaining paths are considered, here there are 1, 2, 3, 4, 5, L equal to 5 path scenario. If L is equal to 5 paths, the deep fade occurs in the two paths. Maybe this is the path 1 and maybe this is the path 2. Even though these two paths are removed and consider remaining three paths, the signal will be, the same signal is transmitted. Calculate what is the SNR of this path and calculate what is the SNR of this path and what is the SNR of this path. So even though if the two links or the two paths are removing, our transmitted signal is received at the receiver side because there is a multiple links in between the transmitter and the receiver. So that's why same information reaches the receiver on statistically independent channels. Channels means paths. So start independent. Suppose this path is independent of the, because the all paths are not correlated because they are independent paths. So one path is not depends upon the next path. because every path is, they are independent paths. So they are transmitting the signal, and a receiver has received the transmitted signal without any deep fades. So deep fade means not all times deep fade occurs. If the channel is in very bad condition, so in that particular scenarios, suddenly at any one point of time, the amplitude of the transmitted signal is suddenly decreases. So suddenly decreases means amplitude is equal to, generally it is equal to zero amplitude. So the signal is completely lost at that particular instant. So that's why definitely if the signal is lost, means the SNR or the probability of error is equal to, or signal strength is very less and the noise strength is more. So that's why if the BER performance is degraded. So to improve the performance of the wireless communication system link, or to improve the performance of the wireless communication by using the diversity. This is the principle of diversity. If one radio path undergoes deep fade, another independent path may have a strong signal. So by having more than one path to select from, both the instantaneous and average SNRs at the receiver side may be improved. So here for each and every path except the deep fade paths, to calculate the individual path or individual channel, SNRs are calculated. So what is meant by SNR? Signal power by noise power. So signal power by noise power at the output of the receiver, or output signal to noise ratio. So the uh, signal output signal power to input signal power. So what is output signal power? It is a instantaneous signal power by average noise power. Calculate instantaneous output signal power to average noise power is called as a SNR, signal to noise ratio. How to improve the signal to noise ratio, or how to maximize the signal to noise ratio? Once the signal to noise ratio is maximized, so the bit error rate is improved, or improving the bit error. Improving means error is less and the signal power is more. So that's why the BER is improved. And to maximize the SNR. In the digital communication, one of the receiver is, it is a matched filter receiver. In the matched filter receiver, what is the SNR maximum equation? So modulus of, suppose the signal power is equal to, maybe notation of the signal is G of T is the signal. So this is norm G of T square by, and average noise power. So this is the average noise power is SNR maximum. How to maximize the signal to noise ratio at the output side? Similar concept is used here in the diversity techniques also. How to maximize the signal to noise ratio? To calculate the maximum signal to noise ratio at each and every path except deep fade paths. Deep fade paths are neglecting and the remaining paths are considered, and calculating the individual paths signal to noise ratios, and what is the maximum signal to noise ratio of each and every path. At the receiver side to decode the signal. But the channel is a multipath wireless communication system. So the multipath wireless communication fading channel coefficient is equal to H is the fading channel coefficient, and X is the maybe transmitted signal, and the noise is, suppose without fading channel, consider first non-fading channel AWGN. So the noise is equal to N. It is called as a Y is equal to, generally in wireless communication system, the received signal is equal to Y is equal to HX plus N. H is fading channel coefficient or a channel coefficient, and X is the transmitted symbol, and N is AWGN noise. To calculate SNRs at the receiver side. So to improve the so SNR at the receiver may be improved. Provide across maybe the transmitted signal in the time or frequency or space. Suppose need for diversity. So I will explain this point in the next slide. Time, frequency, space means what? Need for diversity. So diversity need is the first point is compensate fading channel impairments. What are the impairments? Attenuation and delay, decreasing of the amplitude and phases, phase changes and amplitude changes. All these are the impairments. So compensate fading channel impairments is one of the need by using the diversity techniques. And second one is reduce the depth and the duration of the fades experienced by a receiver. So by using the diversity, so to reducing the duration of the fades are also experienced by a receiver. And improve the link quality. Link quality means wireless communication system link performance is improved by using the diversity technique. So without increasing the transmit power and also without increasing the bandwidth of the channel. So whatever transmitted power is used and whatever channel bandwidth has given without any change of the channel bandwidth, without any increasing of the transmitter power, how to improve the wireless communication system performance and how to improve the wireless communication link by using this diversity concept is used at the receiver side. Diversity techniques are used at the receiver side only. And types of diversity already I have explained small scale fading and large scale fading. So the large scale fading is caused by shadowing and path loss, and small scale fading occurs due to rapid fluctuations as the mobile moves over a shorter distances. And microscopic diversity and macroscopic diversity. Microscopic diversity is used to reduce small scale fading effects. To reduce the small scale fading effect by using micro diversity technique. And macro diversity is used to reduce large scale fading effects. To reduce the large scale fading effects, macro diversity technique is used. To reduce small scale fading effects, microscopic diversity. Again, this microscopic diversity, there are different types of microscopic diversity techniques. And diversity combining techniques. So one of the actually three different types of diversity, not only three, there are four diversity combining techniques. What is the diversity technique and what is meant by diversity combining techniques, I will explain in further slides. In the diversity, one of the technique to improve received signal quality, transmitting multiple copies of the signals in different paths or branches or channels. So the signals propagating through different paths will have different SNRs. Already I have explained in the previous slide. So paths must be highly uncorrelated or not correlated. They are independent paths. So these are the important points related to the diversity. To improve the received signal quality, to improve the received signal quality improves means automatically wireless communication link performance is increased. And calculate SNRs of different paths, and all paths are uncorrelated. And suppose if it is a correlated, if the one path is affected by the one path signal is affected by the another path signal. Actually, one of the research area is suppose for consider a multipath fading channels, the correlation coefficient rho is equal to 1. If the rho is equal to 0.1 and 0.2 or 0.3 by varying the rho parameter, and what is the performance of SNR versus BER is one of the performance metric. Generally, in the wireless communication, the important performance metric is SNR versus BER. Not only SNR versus BER. So, if there are a different correlation coefficient is changes and calculate SNR versus BER for different fading channels and with fading and without fading and comparison of all fading channels and with diversity and without diversity and also MRC using MRC diversity technique with the help of the BPSK modulation or QAM modulation or index modulation. Nowadays 5G and beyond 5G index modulation techniques are used. So index modulation, what is the purpose for index modulation means if the more number of information bits are transmitted. Suppose if it is BPSK, at a time only one bit is transmitted. Suppose if it is QPSK, at a time 2 bits are transmitted. Suppose if it is a 8 QAM or 4 QAM, 8 QAM, 16 QAM, 32 QAM, 64 QAM. So suppose if it is a 8 QAM, at a time 3 bits are transmitted. Along the 3 bits, additional information bits are transmitted by using the index modulation. So by using index modulation technique to improve the spectral efficiency and to improve the energy efficiency. Suppose in MIMO applications, so in MIMO, multiple transmitting antennas and multiple receiving antennas are used. Even in the massive MIMO also, the minimum number of transmitting and the receiving antennas are 64. Suppose if it is a 63, it's not a massive MIMO only. And at least minimum 64 transmitting antennas and 64 receiving antennas are used. Such a system is called as a massive MIMO system. But one drawback in the MIMO, if the number of antennas are increases to improve the performance, but the energy efficiency is decreased. How it is decreasing the energy efficiency? By increasing the transmitting antennas in the MIMO system. Suppose for example 4x4 MIMO. In 4x4 MIMO, 4 transmitting antennas and 4 receiving antennas are used if each and every antenna is transmitted by the signal. So all 4 antennas are active, transmitting antennas and the receiving antennas also. So if each and every antenna, it is having some passive elements. So due to the antenna, each and every antenna is active. So they dissipate power. So suppose there are 4 antennas are dissipate powers and they are using in the passive elements. So the overall energy is decreases. So that's why energy efficiency is decreased in MIMO system. How to improve the energy efficiency means out of 4 antennas, like 1, 2, 3 and 4 antennas. Suppose one antenna is active and the remaining 3 antennas are silent. Even in the receiving side also, one antenna is transmitted, only one antenna is receiving signal and the remaining 3 antennas are silent. So the to dissipate a power of only one antenna, not other antennas. So that's why the energy efficiency is improved and the spectral efficiency is also, actually this is the concept of index modulation. In the index modulation, if the more data bits are transmitted, so modulation order transmitting the bits and also if the antenna is also transmitting some bits. That is one of the concept, that is one of the lecture in index modulation techniques. Actually, index modulation techniques are entirely different from the normal digital modulation techniques. This concept is different. So at a time, only one antenna is active. Suppose in the spatial modulation, one antenna is active. It depends upon the techniques. Spatial modulation is one of the index modulation techniques. And the quadrature spatial, there are different types of index modulation techniques. But here the diversity is used to improve the link performance or to combat the fading effects. So first one is the micro diversity. In micro diversity is used to combat effect of small scale and the 5 most common methods. under micro diversity, there are different methods. One is spatial diversity, time diversity or temporal diversity, frequency diversity, polarization diversity, angular diversity. So in spatial diversity, what is meant by spatial? Several antenna elements separated in space. Suppose in time diversity, transmission of signal at different times. So to transmit the signal, transmission of the signal at a different time slots. For time slot T1, one signal is transmitted. Time slot T2, the transmission of the signals, but the signal is the same signal. The same diversity means the same information is transmitted by the transmitter through a multiple paths. If the transmission of the signal at a different time slots, that is called as a time diversity. And frequency diversity means the transmission of signals at different frequencies. So here in the previous slide, time, frequency and space, each one is called as one of the diversity technique. In frequency, transmission of signals at different frequencies. And polarization diversity means multiple antennas with different polarizations. And angular diversity means multiple antennas with different antenna patterns if the pattern is different. And macro diversity means large scale fading effects are reduced. So by using macro diversity. Under micro diversity, there are some combining techniques also, diversity combining techniques. So one is selection combining, and second one is maximal ratio combining, and the third one is selection combining is one of the diversity combining technique. MRC, so in the researchers, they are using combining techniques only, not for other diversity techniques. Selection combining, MRC diversity, and equal gain combining technique. So generally, these three are used in the research papers, like in the wireless communications. So diversity is the area of the research or one of the object, not entire thesis is the diversity. One of the objective is diversity techniques, selection combining, MRC, using selection combining, what is the performance of the system? Like suppose, for example, it is a 4G system or OFDM system or NOMA system. By using selection combining, what is the performance? By using MRC diversity technique and EZC, individually calculate the performance by using different digital modulation techniques, BPSK, QPSK, QAM, and using maybe channels are changed, or maybe if any multi-carrier system at the transmitter side, by using a error control coding techniques, generally in all the modulation waveforms, they are using convolutional coding techniques are used. Instead of convolutional coding, either LDPC or turbo are used. This is one of the object of a wireless communication. And changing the modulations is another objective. And diversity changes. Suppose individually verify the system performance, and by combining, suppose selection combining and like it is a hybrid systems, selection combining and MRC is clubbed, selection and EZC, and the comparison performance, selection and MRC and EZC, what is the performance plot, and hybrid combining techniques, what is the performance. So if you perfect in one system, like either OFDM or NOMA or any like massive MIMO or MIMO system or 5G waveform. Suppose if you are working on physical layer, first you can select a system. First, each and every block is simulated using MATLAB simulations. So instead of convolutional codes, you can incorporate other coding techniques. So instead of the AWGN channel, you can introduce or you can incorporate fading channels. So instead of a modulation technique, you can change the BPSK, QPSK and QAM. And instead of at the receiver side, instead of a like a general detector, detector, and combining techniques are also used. So these are the research areas in wireless communications. So first, thorough understanding of a system and easy to incorporate or changes the blocks and write a different SCI papers. So diversity combining techniques. First one is a selection combining. What is actually this technique is? It is a very simple technique, but in the performance point of view, selection combining is compared to MRC. Selection combining is compared to EZC. It will get a poor performance. What is meant by selection combining? At least maximum I will try to finish mathematically MRC, because the MRC diversity techniques gets a good performance when compared to the other diversity techniques. That's why I will concentrate on MRC. If time permits, I will explain EZC also, because I have half an hour time. The selection diversity. What is meant by selection diversity? In the selection diversity, this is the basic block diagram of a selection diversity combining technique. So, what is meant by combining means, okay, at the time of MRC, I will explain. So, selection diversity is one of the Hello. Okay, in the selection diversity, there are M multiple paths or M antennas are used. So each and every path received a signal. Actually, G1, G2, GM are gain of the antennas. Antenna 1, antenna 2. When we are transmitting the signal means, we need antennas. So there are multiple antennas or the multiple paths. The signal is transmitted at the receiver side. The first path signal is received, and this is the variable gain of the antenna, and the received signal from the first path calculate what is SNR here. So the SNR, and the second path signal to calculate the SNR. So each and every path to calculate the SNR, out of all paths, to select any one of the path. So the selected path is the highest SNR path. So the block diagram of selection diversity is similar to the shown above. This is the simple technique, and M diversity branches are links with M demodulators whose gain can be adjusted to provide same average SNR for each branch, and branch with high SNR is selected. Out of all branches, to select highest SNR path. Suppose the second path is the highest SNR path. Only this path is selected and neglecting all other paths and demodulate, and what is the output? Transmitted output is demodulated at the receiver side. Selection means to select out of M paths which path SNR is high or high SNR is selected. So that's why the technique is very simple. Suppose we can consider 4 paths. So calculate 4 paths SNRs. Out of 4 paths, which path SNR is maximum. So that path will be selected and decode it, and to recover the original transmitted signal. So that's why selection diversity means to select the high SNR path. And next one is scanning diversity. Actually, feedback or scanning is one of the combining technique, but this is not a familiar technique. But what is the procedure is, this is also similar to selection diversity. M signals are scanned in a fixed sequence until one is found to be above a predetermined threshold. Here, to fix a predetermined threshold, each and every branch, the signal is scanned. If the received signal SNR is above the threshold or below the threshold. Suppose if SNR value is false, then the scanning process is initiated again. takes more time than selection diversity, because it is a scanning process to scan the signal many times. So if the SNR is above the threshold or below the threshold, if it is above the threshold, signal is considered, or above the threshold means it is a high SNR signal, but the process is scanning. Suppose first receives, if it is below the threshold, again to repeat the procedure. So until the received signal SNR is above the predetermined threshold, the process is repeated. That's why it will take a lot of time scanning the process and initiated again and again. So that's why this is the more complex than the selection combining. So, and the time is also more time than selection diversity combining. But the simple to implement, only one receiver is needed here, not number of receivers. So because predetermined threshold and only one receiver. And this is the very important maximal ratio combining technique. In the maximal ratio combining technique, what is meant by combining? I will explain. First, combining. Yeah. So in this diagram, is it visible to you, participants?
Yes, madam.
Yeah. Here we have transmitter and the receiver. This side is the receiver. Actually, only one transmitter. This system is called as a single input and multiple output SIMO system. Single input, multiple output, and multiple input, single output, and multiple input and multiple output. There are different types of the systems. So only one transmitter, and there are two receivers, and there are two paths. So the channel coefficient is H1 is the channel coefficient, and H2 is the channel coefficient, because L is equal to two paths. So L1 and L2, there are two paths and the two channels. Here, AWGN noise is added here. So N1 is equal to AWGN noise. So at the receiver side, before the receiver, when the signal is same signal is transmitted by the two paths or multiple paths, multiple means here only two paths. So this path signal is added with the through the channel. The signal is transmitted through the channel. The channel noise is added to the signal, and Y1 is equal to H1, and the transmitted signal is equal to, general equation is Y is equal to Hx plus N. So Y1 is equal to, there are two paths, Y1 and Y2. Y1 is equal to fading channel coefficient, or a channel, not fading channel coefficient is H1, and the transmitted signal is X, plus noise, AWGN noise is N1. So Y1 is equal to H1X plus N1, and Y2 is equal to H2X. Transmitted signal is same, X and X, plus N2. So this Y1 and Y2 combining means, actually here up to here, so there is a channel output is equal to Y1 and Y2. So the channel output, or Y1 from the channel output and Y2 from the second channel output, these two are multiplied with the coefficients. Coefficient means weight vectors. So in both equal gain combining and MRC maximal ratio combining, the signals are received from the channel Y1 and Y2 is multiplied with the weight factors. So multiplied with the weight vector or a weight factors. So that is equal to W is the weight vectors. So how it is calculated, I will explain in MRC. So the similar procedure to EZC. What is the difference between MRC and EZC is, these weight vectors are same weight vectors are multiplied with Y1 is equal gain, equal means the weight vector is same equal weight vector is multiplied with the Y1 and multiplied with the Y2 is equal gain combiner. Maximal ratio combining means, so the y1 is multiplied with the weight vector and y2 is multiplied with the weight vector. These two weight vectors are different in MRC diversity technique. In MRC, the weight vectors are different. Channel 1 weight vector and channel 2 weight vectors are different. In equal gain combining, the weight vectors are same weight vectors. So this is the basic difference between MRC and ECC. What is meant by combiner? So after multiplying the weight vectors, the weight vector output is y1 bar. Y1 bar is equal to y1 multiplied with the weight vector and y2 multiplied with the weight vector. So y1 bar in terms of the vector notation, y1 bar and y2 bar, both y1 bar and y2 bar are added together, are combining together, is called as a combining technique. So the two paths outputs are combining, because in the selection combine, we are not combining any signal. So if there are multiple paths, each and every path SNR is calculated. Out of all paths, which path SNR is maximum, so that path is selected. But here, calculate first path SNR and calculate second path SNR, but both the paths are added together, are combined together to generate a summed signal, or by adding of y1 and y2, or y1 bar plus y2 bar is equal to y bar is the output of the receiver. So the combining means combination of the or adding of multiple paths signals together to generate a one signal. Actually, this SNR and this SNR, both SNRs are added. So what is the total SNR? Suppose individual paths SNRs and combined path SNR, here SNR is calculated. Which path SNR is more? Which path SNR is more? So the first path SNR and the second path SNR. Just a minute. Just 1 minute. So here, am I audible to you?
Yes, madam.
Yes, madam. Yes.
Yeah, here y1 bar and y2 bar. Suppose this SNR is equal to maybe 20 dB, or this SNR is equal to maybe 30 dB. 20 plus 30, it is equal to 50 dB. The overall SNR is increases. So to combine the both the SNRs and calculate the total SNR, and how to improve this SNR and how to recover the signal. So this is called as a combining techniques. Individual paths SNRs are like calculated by combining all the paths to improve the signal strength. So that's why actually equal gain combining and selection compared to the MRC and ECC, compared to the selection gain combining technique. So the overall performance is more here because the signal strength will be more. So in the maximal ratio combining here, this is the basic block diagram of maximal ratio combining. So whatever before showing, that is also called as a maximal ratio combining diversity combining block diagram. So with weight factors are also multiplied here. So there is a multiple antennas and multiple paths are receiving the signal, and multiplied with the weight factors here, and calculate the gains. SNRs. SNR is gamma 1, gamma 2, gamma 3, and so on, gamma M SNRs. and each and every gain, and also because every antenna we have a gain, and multiplied with the like weight factors, and they are co-phased, all are in the same phase, are aligned the signals same phase, and gamma m is equal to signals from all m branches are weighted according to the individual SNRs, according to the individual SNRs, and summed. Weighted means weight factor is multiplied. And output SNR of gamma m. Gamma m is the individual SNR. Sum of all individual SNRs is equal to gamma m is the total SNR. So always the gamma m is greater than the threshold value, because this gamma m is always greater than the individual SNRs and the predefined threshold. Definitely this will be more. So used in the digital receivers, best of all other techniques, actually MRC. So now I will start mathematically how to design SNR equations mathematically. So we know the mathematical SNR equation. It is easy to simulate using MATLAB. A drastic dip in the signal of wireless channel indicates a deep fade. Drastic dip in the signal. Signal means amplitude. The amplitude of the signal is drastically decreased, or drastic dip in the signal amplitude of wireless channel indicates it's a deep fade. Already I have explained. Will occur if the multipath co-channel coefficient drops below. So diversity means a method to improve the performance of the wireless communication. Suppose there is a transmitter and receiver. Here there is a deep fade occurs. So drastically decreasing the signal amplitude. And so this is the single input to multiple output. So the diversity is obtained here. Because the name of this diversity is called as a, if the more number of antennas are connected at the receiver side, it is called as a receive diversity. And so here, suppose for example, two antennas at the transmitter side, two antennas at the transmitter side, and only single antenna at the receiver side. This is called as a transmit diversity. So this is the receive diversity. The diversity is obtained at the receiver side. Here the diversity is obtained at the transmitter side. So in the MIMO system, the diversity is obtained in both the transmitter and the receiver side. That's why this is called as a transmit receive diversity. And as the number of antennas complexity, number of antennas are increases means complexity increases, but the performance is improved. So general in wireless communication, the received signal is y equal to hx plus n. H is the channel coefficient, and x is the transmitted signal, and n is the channel noise. Y1 is equal to h1x plus n1. And y2 is equal to h2x plus n2. h1 and h2 are channel coefficients, because this is equal to L is equal to two-path scenario. And this is also called as a single input to multiple output system, because h1 and h2, y1 and y2 means the transmitted signal is single transmitting antenna and two receiving antennas. So the channel type is AWGN channel. With AWGN channel, mean equal to 0 and variance is equal to sigma square. And expectation of AWGN channel noise is expectation of n square is equal to expectation of n2. Okay, I will explain that point in the later stage. So there are many techniques to study the outcomes. Some of them are maximal ratio combining, equal gain combining, and selection combining. So this is the basic block diagram, and this is called as a block diagram of a maximal ratio combining. We have a single input and multiple output system. So there are suppose m paths, so paths to receive y1 and multiplied with the weight factor. So y2 multiplied with the weight factors. And by combining all the signal outputs are added and to generate a new signal. So to recover at the receiver side. And If Z1, Z2, instead of Z1 and Z2 means weight factors. You can write instead of W1 and W2 are the weight factors. Z1, Z2 or W1, W2 or whatever notation of the weight factors. Here V1 and V2 are they have written. So that is just for the notation only. If W1, W2 are given maximum weightage, we call it as MRC, maximal ratio combining. The maximum weight is multiplied with each and every part. And these weights are different because already I said equal gain combining means the weights are equal. And MRC diversity technique weights are different path weights. First path weight factor is different and second path weight factor is different. They are not same. So considering X be the real equal weightage, we call it as EGC. If it is a equal weight, so it is a equal gain combining. So the previous equation, like this equation, it can be right in terms of the vector notation. Y1, Y2 is equal to H1, H2 into X plus N1, N2. So this is called as a received vector. Y is the received signal. Y is equal to Hx plus N. So that in terms of the vectors Y1 and Y2, in terms of the channel coefficient, right, in terms of the vectors H1, H2, and the noises are N1 and N2, noise vector. So we have two paths, L1 and L2, so that the received signal need to be combined. The two received signals, there are two paths received signal need to be combined or need to be added. So that is equal to complex conjugate of Y is equal to W1, Y1. Y1 is multiplied with the weight factor. So Y1 is multiplied with the weight factor. Y1 multiplied with W1 plus this is the first path signal. And the second path signal is Y2 multiplied with the W2. So write in terms of the W1, W2 and Y1 and Y2. Actually, this is not a row vector, it is a column vector. So that's why write transpose. W bar transpose because vectors. So this is the Y bar. W bar transpose, instead of transpose, you can write Hermitian also. W bar transpose into Y bar, which is equal to, what is Y bar? Y bar is equal to equation number 1. Equation number 1 is substitute here in place of Y bar. W bar transpose is equal to H bar X plus N bar. So our aim is how to calculate the SNR mathematically. So now I will explain calculation of the SNR of each and every path. So W bar transpose Y bar. Y bar is equal to H bar X plus N bar. W bar transpose multiplied with H bar X plus N bar. W bar transpose H bar X plus W bar transpose N bar. So what is this term? If it is not having any N, because it is a signal component. So the first term is signal component and the second term is N bar is, it is a noise, AWJ noise, multiplied with the weight factor because this is the noise component, signal component and a noise component. So calculate what is SNR. SNR is equal to signal component by noise component. So the signal component is here W bar transpose H bar X is the signal component. So already I have explained using in the matched filter detector or any SNR calculation, the numerator is instantaneous signal power by average noise power. So the instantaneous and average. Average means expectation. Instantaneous means square of the signal. So here W bar transpose H bar, same equation. W bar transpose H bar mod square into X is the transmitted signal power. So P is the transmitted signal power. And denominator is noise component. What is the noise component? W bar transpose N bar. W expectation of W bar transpose N bar square, because it is a instantaneous signal power and average signal power. Expectation of, actually this can be written as this one, expectation of N square or mod N square. So this is to simplify the first denominator. W bar transpose N bar, this denominator. So W bar transpose N bar is equal to W bar transpose is W1, W2 vector, this one. It is called as a W bar transpose. Multiplied with N bar. N bar is equal to noise vector, N1 and N2. Path 1 and path 2 noises are N1 and N2. So both are multiplied, W1, N1 plus is W2, W2, N2. And expectation of like W1, N1 plus W2, N2. So expectation square. So this is W1, N1, W2, N2 whole square. This is A plus B whole square form. Expectation of A square, W1, N1 square. And expectation of like W2 square, N2 square plus 2AB, 2 W1, W2, N1, N2 whole expectation. So it is separated the terms. Expectation of N1 square. W1 square is take common, expectation of N1 square. Here W2 square common, expectation of N2 square. 2 W1 W2 expectation of N1 and N2. Expectation of N1 square is equal to expectation of N2 square is equal to variance. And expectation of N1 into N2 is equal to 0. These are the assumptions. So the expectation of path, first path noise and expectation of second path noise to variances. So that's why it is equal to expectation of N1 square is sigma square plus W square into expectation of N2 square equal to sigma square, because they are uncorrelated channels. So that's why 2 W1 W2 expectation of N1 and N2 is equal to 0. So W1 square sigma square plus W2 square sigma square, and so take common sigma square, W1 square plus W square. Sigma square into W1 square plus W2 square is equal to norm W bar square. So W bar is equal to W1 and W2. So what is norm W bar square? W1 square plus W square. So sigma square into norm W bar square is called as a denominator. And right of the numerator. So the denominator is W bar transpose H bar square is equal to W1 W2 H1 H2 whole square. W bar H bar square. Norm, please unmute. Norm W bar square into, because this is the dot product. So norm W bar square into norm H bar square cos square theta. Suppose SNR is equal to, we know the numerator. So the numerator is W bar square. Actually, this is the numerator. W bar transpose H bar whole square. So that can be written as, this is the term. W norm W bar square norm H bar square into cos square theta into P upon, and denominator is already we have derived. Denominator is sigma square into norm W bar square. So norm W bar square cancelled. Norm H bar square into cos square theta into P by sigma square. So P by sigma square into norm H bar square into cos square theta. So where theta is equal to maximum or theta is equal to 0, cos theta is equal to 1, it is equal to square, it is equal to 1, P by sigma square into norm H bar square. So P by sigma, what is norm H bar square? H1 square plus H2 square. So SNR maximum when theta is equal to 0. So norm H bar square into SNR. SNR is equal to P by sigma square. What is P? Signal power. And what is sigma square? Noise. So signal by noise is equal to SNR. So norm H bar square into SNR is the maximum SNR of a MRC diversity combining technique path. So what is the weight of MRC? W bar is the weight. We don't know the weight. So H bar is equal to channel coefficient. And SNR is transmitted signal power and variance of the noise. But what is weight of MRC? Weight of MRC is W bar. What is W bar? H bar by norm H bar. So H bar is equal to H1 H2 into 1 by norm H bar is equal to H1 square plus H2 square. So when theta is equal to 0, W bar, H bar in the same direction. And W bar should be unity. So 1 by H1, 1 by H norm H bar, H1, H2. So this is called as a weight factor. Suppose if the transmitted signal is a complex coefficient, W1 complex conjugate of W1 Y1 plus complex conjugate of W2 Y2, and the remaining procedure is same. So what is the maximal ratio combining diversity technique SNR means? So this is the SNR equation. What is the weight factor? If SNR is calculated or Y1 and calculate S1, Y1 is multiplied with the weight factor. The weight factor equation is, this is the weight factor equation. So just I will take 5 minutes to explain one numerical example using MRC diversity technique.
Alekia madam, please unmute it now, madam. Alekia madam, please.
So using MRC diversity.
Alekia madam.
Unmute it, madam. Please.
Using MRC diversity technique, we have in the MRC already we have taken single input multi output because the diversity obtained here. So what are the channel coefficients? Already in this example they have given channel coefficients H1 and H2. So H1 is equal to 1 by root 2 plus H2, 1 by root 2 plus 1 by root 2 because it is a complex signals. And H2 is equal to, they have given channel coefficients, and also calculate what is the SNR, whether the SNR is improved or maximum or not, we will check using this example. So H1 has given and H2 is also given. Calculate the SNR of maximal ratio combining. Mathematically, I have explained, but numerically consider one example and how to calculate the and what is the exact value of the SNR numerically. So H1 and H2 is also given, and Y1 equal to H1x plus N1, and Y2 is, Y1 is equal to, substitute in place of H1. So this equation, and 1 by root 2 plus 1 by root 2 j is H1 x plus N1. Y2 equal to, substitute H2. This is the Y2 equation. And expectation of N1 square equal to expectation of N2 square is equal to sigma square. So in this example, they have given variance is equal to 1 by 2 is the variance represented in the vector form. Represented in the vector form means write down received signal vector is Y1 and Y2, and the transmitted channel coefficient vector is H1 and H2. These two are, this is H1 and this is H2. Hx plus N equal to, there are two paths, N1 and N2. Y bar equal to, in this equation, substitute given H1 and H2. Using MRC, what is the weight vector? W bar equal to H bar by norm H bar is the weight vector. What is H bar, norm H bar? First, to find norm H bar. So already they have given H1 and H2. Root of H1, root of mod H1 square plus mod H2 square is equal to norm H bar. So what is H1 and H2? H1 is equal to 1 by root 2 plus 1 by root 2 J is H1, and H2 is equal to 1 by root 2 minus 1 by root 2 J is equal to H2. So H bar is equal to, so this is the H1 and H2. So calculate this one. H bar, norm H bar equal to H1 bar square plus H2 square. H1 is 1 by 2 plus 1 by 2J, 1 by 2 minus 1 by 2J. So it is a square. So 1 by root 2 square plus 1 by root 2 square plus 1 by root 2 square plus 1 by root 2 square. So root 2 square is equal to 2. That's why I have written 1 by 2 plus 1 by 2 plus 1 by 2 root 2. So sorry, root 2 is the H bar. And calculate weight vector. Weight vector W bar equal to H bar by norm H bar. So H bar is equal to 1 by root 2, and norm H bar is equal to, norm H bar is, this is the norm H bar. So direct matrix is the norm H bar, H1 and H2. So now what is the SNR equation? Already this equation is derived in the previous derivation, MRC derivation. W bar H, W bar not H, even right transpose. W bar transpose into H bar norm square P by sigma square into norm W bar square. So what is P by sigma square is the SNR, and W bar transpose H bar whole square into P. So W bar, in place of Hermitian, you can write transpose, both are same. W bar transpose into H bar. So we know the W bar transpose. This is the W bar transpose into H bar. To simplify these two. And finally, we got the value of W bar transpose H bar is equal to root 2 and square, because this is the square. So root 2 square is 2. Norm W bar square is equal to W1 square plus W2 square. So what is W1 and W2? So here we have calculated um, H1 and H2 square. So it is equal to, finally, W norm W bar square is equal to 1. Norm W bar square is equal to W1 square plus W square, and 1 by 2 into H1 square plus H2 square plus H1 square plus H2 square. H1 is 1 by 2 plus 1 by root 2 plus 1 by root 2 J. So it is simplifying, we got 1. So SNR is equal to, this is the SNR equation we have derived in place of Hermitian, W bar transpose P into what is W bar transpose H bar? It is equal to W bar transpose H bar square equal to 2 by sigma square. Sigma square is equal to, already they have given 1 by 2 is the variance, noise variance. And W norm W bar square is equal to 1. So which is equal to 4P is the SNR for MRC diversity technique. 4P means P is what is transmitted signal power. The transmitted signal power is 4 times the transmitted signal power. So the overall SNR is increased or not? Or overall power is increased or not? Transmitted power. Power means in terms of the strength, not transmitted power. The signal power is P and 4 times the signal power. So the SNR is maximized, or the signal strength will be increased in terms of the power or in terms of the energy. So the signal originally without MRC diversity technique, the transmitted power is only P is the transmitted power. With diversity combining technique is used to, it increase the signal strength. So increase, maximize the signal strength. So to maximize means SNR is maximized. So that's why the overall bit error rate performance is decreased. So I will stop it here. In the equal gain combining, same procedure, but the weight factor is different. The weight factor of equal gain combining is complex conjugate of H bar by mod H1, complex conjugate of H2 by mod H2. So this is the difference. This is the weight factor of ECC. The remaining procedure is same procedure. Same, we can calculate what is the SNR of ECC means this is the SNR. P by sigma square is the SNR. Actually in the MRC, what is the SNR of MRC? P by sigma square times of, what is the formula for MRC? P by sigma square times of H bar, norm H bar square. So similarly here, L I is equal to 1 to L means here not consider two paths, L paths are considered. That's why norm H square by L is equal to number of paths. So this is the SNR, maximized SNR ECC equation. So actually this is the derivation. Okay, I will stop here. Any doubts, participants?
No, ma'am.
Participants, any doubts?
Dear participants, if you have any doubt, please, you can ask some questions.
Okay, okay.
Who's that? Hello?
Okay, sir.
Okay, ma'am, I would like to say thank you. Thank you for your presence. Thank you for sharing time.
Madam,
Thank you.
once again, put the feedback link, madam.
Feedback link will be shared, sir, in a short while. Just
Just
in
send
short.
one, sir, please.
We are there only. Any participants, if you want to?
Thank you, Anuradha madam.
Yeah,
Thank you so much, madam. Thank you, madam.
Thank you, Dr. S. Anuradha, ma'am. I would like to express our sincere
Sir,
thanks.
good evening, sir. Sir, good evening, sir.
Good
Actually, today's session, Anuradha madam session only I could listen because of some technical issues, sir.
Okay.
Can you please share 11th session link, sir?
Okay, sir. You have joined earlier session also, no, sir? Means
Yeah,
you,
yeah. So 12th link,
80%.
12th session I have listened, and 11th I could not.
Because 80% attendance is required, sir. If it is 80%, then it's okay. Otherwise, you can message us. The number is there. We will share that link to you.
Okay, right. Thank you, sir. Thank you, madam. Thank you, madam. Anuradha madam.
Yeah,
So
thank
I'm Dr. B.L. Prakash, madam.
Yes.
I think you have done your PhD from our KVS Reddy here, sir.
Yes,
Madam.
yes, yes, sir. Yes, sir.
I saw you and met you in Andhra University, madam.
Yeah.
So thank you for your beautiful session and valuable time, madam.
Thank you, sir.
Okay, thank you, Dr.
Thank you, madam.
Anuradha, ma'am.
Lecture is very informative, madam, and very interesting. You are engaged participant. Thank you so much, madam.
Thank you, madam.
ఇంత బలంగా తెచ్చుకున్నారు
Okay, sir.
Uh,
Shall I leave, sir?
okay, ma'am.
Okay.
On the behalf of ECE department, we extend our heartfelt thanks to you to take time out of your busy schedule and sharing your knowledge and experience with us. We are highly obliged, ma'am. Thank you. Thank you very much, ma'am.
Okay, sir. Thank you, sir. Welcome.
ఇక్కడ లైట్ అంటాం చూడు నాలైట్ అంటాం చూడు దా ఒక్కడే మళ్ళీ
Okay, stop recording.